Hello, this is Adam, and I'm going to talk through a presentation for Week 1 on water properties and watersheds. The first professor that I ever took a water quality class from has a footer on her email that says, "Water is life and quality matters." Water is life, and it's vital to everything that we do. And so first, let's touch on a couple of the most critically important services that water provides. Water is the universal solvent, and we can see it here because of the chemical property, the molecular properties of water. It's very effective at dissolving solutes. In this case, sodium chloride, or typical table salt. I'm also personally very fond of the solutes in this picture. Within the human body, water acts as a solvent that carries nutrients to our cells and carries wastes away from our cells. And as such, water is approximately 70% of the human body. In addition to that, water plays a critical role in the food and fiber, growing the food and fiber that we depend on for our bodies. If we look at this most fundamental equation for photosynthesis, we see that water, along with carbon dioxide, is a key element going into the creation of simple sugars and oxygen. As we can see here, where this wheat crop is growing in central Montana, it is using water that it is taking up from its roots, combining that with carbon dioxide from the atmosphere to produce that biomass that we rely on. Sanitation is a service that water provides as we wash our hands and flush our toilets, and for better or worse, send our wastewater to water treatment plants that treat and then dispose of that water, in most situations, into our streams and rivers and send that downstream. And again, we rely on water to carry that away. And so when we look at the Earth's surface, we have those obvious places along these stream corridors where water is very important to fish for habitat. But we also see a lot more subtle indications. The riparian area here, where you have all these willows and cottonwoods, is obviously very important, where those phreatophytes are using water out of the shallow groundwater. But possibly even more subtly is the role of water in the shape of these channels that have carved these canyons, and also the distribution of vegetation on the north versus south facing aspects of these slopes. On the north on the north aspect here in the northern hemisphere, where there's less solar radiation, the slopes are wetter and have more vegetation, as opposed to the south-facing aspects where they get drier and there's less vegetation. So again, water playing critical roles throughout this landscape. Let's take a closer look at that molecular structure that I mentioned for water. Water, being H2O, obviously has 2 hydrogens and 1 oxygen. And something unique about this molecule is that oxygen is very electromagnetic, meaning that it holds the electrons very closely to it, because the electrons are negatively charged, it results in a net negative charge, or a negative pole, around the oxygen molecule, and a net positive at the hydrogen molecules. And because because opposites attract, we end up with this crystal lattice that forms, where the water molecules orient themselves with positive to negative. And this crystal lattice, or this relationship among the molecules, results in a lot of unique characteristics of water. And it's many of these characteristics which really help to make life on Earth possible. Viscosity, or the resistance to flow, is important because of hydrogen bonding, or the nature of this bond that forms among the water molecules because of this polarization. And viscosity is very important in water. When we think about piping or water distribution systems, it's less so in nature, But surface tension is very important. The fact that this water strider is able to sit on top of the water is a result of the molecules being bound together through cohesion by hydrogen bonding. And so cohesion is the sticking together or attraction of the water molecules, as compared to adhesion, which is the water molecules sticking to other things, which is why capillary rise occurs, which is very important in soil and in plants. And specific heat is another element, is another aspect of water that I'll talk about more in a minute, that is controlled by, affected by hydrogen bonding. But it's that cohesion that results in water sticking together, and if when it's sitting on a hydrophobic surface, for instance, like my tablecloth here, it will form together into a perfect sphere, which is pretty cool. And Katie found this video on YouTube where a person put 36 drops of water on a penny because of the cohesion of the water molecules. Hydrogen bonding also affects the freezing and boiling points of water. If we look at other molecules with similar structures, hydrogen telluride, hydrogen selenide, and hydrogen sulfide, for instance, as compared to hydrogen oxide or water, we see that we have this, with decreasing molecular weight, we have a decreasing temperature where both freezing and boiling occurs. But because of the hydrogen bonding and the additional energy required to break those bonds, we have elevated both freezing and boiling temperatures, which allows water to be in both, really a liquid, gas, and a solid state all on the Earth's surface, which helps to make life possible. So again, if it weren't for the hydrogen bonding and that electronegative oxygen molecule, then the freezing, we would expect the freezing and boiling points for water to be very, very cold. And all water on Earth would be in the gas phase. Another interesting characteristic of water, because of hydrogen bonding, is the fact that ice floats, or the solid is less dense than the liquid. If we look at this temperature range here and density of water, up here at high temperatures we have the lowest density, and then as we cool down and the water and the molecules start vibrating more slowly, the density goes up. And that's what we expect. That's typical of most substances. But what's unique about water is that once you reach 4 degrees C, those molecules have slowed down enough that when you start to go to lower temperatures, the hydrogen bonding starts to lock the molecules into this crystal lattice, and the density starts to go back down. And so then you cross the freezing point, and now you've locked in a solid that has all this crystal structure, and makes solid water less dense than the liquid and makes ice float, which is critical because that way we can maintain liquid water in lakes and streams in the wintertime, and fish can persist in those areas. And so from this graph you can take that water is most dense at 4 degrees C, which is, again, a unique aspect of the water molecule. The other thing about hydrogen bonding is that it creates these beautiful snowflakes as a result of that crystal structure from that crystal lattice. The last characteristic of water I mentioned affected by hydrogen bonding is specific heat. And that's the amount of heat energy that has to be added to a mass of a substance in order to increase the temperature. Water is set by definition at specific heat of 1, and then the specific heat of other substances is in relation to water. And the specific heat of aluminum, for instance, is 0.22, which means that water has 5 times the specific heat that aluminum does, or that if you add the same amount of heat to water and aluminum, the aluminum's temperature will increase 5 times more than that of the water. If anyone has ever used a hot water bottle to keep their feet warm in a sleeping bag, then you're relying on the high specific heat of water to keep you warm for longer. If you used a similar weight of metal, then it would not give you heat for as long because it would discharge that heat more quickly. So basically that means that water resists change to temperature. This high specific heat of water is very important when we start to think about climate. And for instance, comparing an inland climate to a maritime climate, if we look at the area where I am here in Bozeman and we look at the annual temperature fluctuation from somewhere around 100 degrees Fahrenheit down to around 0, we get a rather large oscillation relative to that of Seattle, which might go from somewhere around 40 to 70 annual average temperature fluctuation. And why is that? Well, if we look at the annual temperature fluctuation in the ocean there adjacent to Seattle, it is even much lower. So the heat is being absorbed by the ocean in the summertime and is being then emitted in the wintertime and is balancing out the coastal climate or the maritime climate. And those effects are not seen as you move further inland. Okay, so that's the basics of water properties. Let's move on to thinking about watersheds. And looking at this cartoon of a landscape, in order to start thinking about what the definition of a watershed is, we need two things. First, you have to identify a point on a stream network. And so if we think about all of the water that drains to a point on the stream, perhaps near this bridge, then the watershed is the land area that is defined by ridge points or high points on the topography, all of which drains to that point on the stream network. So again, in order to define a watershed, first you need to know what point on a stream network you're talking about, and then you move up in elevation until you find the ridge line where you're otherwise outside that ridge, you're sending water into another drainage or another point on another stream network. So the entire terrestrial surface of the Earth can be broken down into watersheds, and for the United States, this is done with a system the USGS put forth called Hydrologic Unit Codes, or HUCs. And as we look at these largest scale watersheds, or hydrologic boundaries for the United States, we can see one thing right off, which is that the boundaries in most cases do not align with the state lines or the political boundaries. There are a few exceptions in the case of the Rio Grande. Since I am in the western side of the United States, I'll use examples over here where we have the Columbia River separating Washington from Oregon. My favorite state boundary is that between Montana and Idaho, where it's actually a portion of the Continental Divide that separates Montana from Idaho. So as opposed to a river being a boundary here, it's actually a watershed boundary that makes this political boundary. So the majority of Montana is in Hydrologic Unit Code 10, which is the Missouri region, but we also drain a portion of the western part of the state into the Columbia through the Clark Fork River out to the Pacific Ocean. There's also a little piece missing of the St. Mary's watershed up here, which sends water north and to the Hudson Bay. So in Montana we actually send water to 3 different oceans. And so these are the 2-digit hydrologic unit codes for the United States, but it's broken down until we get as far as 12 digits. And so if we look at the next level, for an example, after the 2-digit, the next delineation that people usually talk about are 8-digit HUCs. And so if we look at, we're here in the Gallatin. If we look just across the Gallatin Range to the east, we have the Yellowstone HUCs. So the Yellowstone headwaters up here, this is an 8-digit HUC, and then the upper Yellowstone is just downstream from that. And so again, as we look at the Yellowstone headwaters here, a portion of its watershed boundary on this ridge actually separates the Missouri from the Pacific Northwest. And so up here in Yellowstone National Park, the river flows down and then flows into this other HUC here, which is the upper Yellowstone. We can break it down further, and this is a nested watershed system to a 10-digit HUC. So this Minor Creek here is a 10-digit HUC. And so we've got the same 8 digits as the Upper Yellowstone, and then we've added on 2 additional digits to get to that 10 digit. And then within that we can go as far as 12-digit HUCs and break down. So this Lower Minor Creek or Cinnabar Creek are examples of 12-digit HUCs that are nested within this larger watershed scheme. And it's important to note that these delineations are made based on watershed and hydrologic boundaries, but every HUC is not a watershed in itself. Obviously, this Upper Yellowstone is more of a traditional watershed, but then it flows into, the headwaters is more of a traditional watershed, and then it flows into the Upper Yellowstone, and the edges here of that Upper Yellowstone are a watershed boundary, but they wanted to keep these all approximately the same size, so they cut this off and separated the Yellowstone headwaters from the Upper Yellowstone. So this boundary here is not a ridge line or a traditional watershed boundary. It's a distinction made to have all of the 8-digit HUCs be approximately the same size. And so, for example here, thinking about these nested watersheds, if we've got this Lower Minor or Yellowstone River Minor Creek watershed, that is nested within Minor Creek, which is nested within the Upper Yellowstone, which is nested within the Missouri, which is ultimately a tributary of the Mississippi River. And so if we want to understand water quality, this nested watershed concept is very important because it's a compilation of all of the water quality from these smallest watersheds that come together to make the quality of the larger rivers. So in thinking about this watershed delineation, let's take a closer look right here at the Gallatin versus the Upper Yellowstone. And so the Gallatin, Bozeman is down here, and the Upper Yellowstone that we were just looking at is over here, and this is the ridge or the watershed boundary between those two watersheds. And if we've got a drop of water that falls near that ridge, if it falls just to the east, it flows down the Yellowstone River, and if it flows just to the west, it falls into the Gallatin and then flows up into the Missouri, and the 2 drops of water don't see each other again until they cross the North Dakota border where the Yellowstone meets the Missouri. So if we look here at Highlight Peak, this watershed boundary is this ridge line running right across here. And if we think about that in terms of a topographic map, which is typically how we will look at elevation on a map, so these lines are all lines of equal elevation, and we have Highlight Peak here, and water flows off perpendicular to those topographic lines, and Highlight Peak sends water in 4 different directions. And so this watershed delineation is critical if we want to start to think about water quality, because in each of those watersheds we might have different land uses and different landscape characteristics which are going to affect the water quality that we see. And so going back to this 12-digit HUC example, the Yellowstone River Minor Creek is again in the headwaters of Minor Creek in the Upper Yellowstone. And once we have this watershed delineated based on topography, and we want to understand the water quality that's coming out of the creek down here, we can overlay different data layers. In this case, we've got an aerial image, and we can start to think about what the land cover is in that watershed and how that's interacting with land use, perhaps, to result in water quality coming out the bottom. In addition to land use and land cover in these watersheds, one of the biggest drivers for water quality is discharge and precipitation, the water balance, the amount of water moving through those watersheds and through the hydrologic system. And so this is a graphic of the water cycle, something we've all seen many, many times. What it might be different about this one is that it has indication of the magnitude of the pools of water in different places across our planet in thousands of cubic kilometers. So in the boxes here, the largest pool on Earth is the ocean, and then we've got a large fraction in glaciers and snow. At any one time, a much smaller number, just 2,000 cubic kilometers of water at rivers. In rivers, the other thing that's depicted here are the fluxes, or the movement of water between different pools. And so we start up here with precipitation. We have 111 cubic kilometers falling every year, distributed between snow and rain like this. Immediately, more than half of that is lost to evapotranspiration off of the terrestrial environment before it even has a chance to flow back into the rivers. So the difference here between river flow or the addition of river flow to evapotranspiration is what we got in precipitation. And there's a lot of other really interesting elements in here that you can look at. The quantity that is in soil moisture, for instance, and groundwater at any one time. Permafrost is represented. And so this coupled with your readings will help to inform your assignment and your discussions for the week. Thank you for your attention.